In this video, we'll be talking about two more factors that can affect the rate of a reaction in terms of collision theory. So the first one is temperature. So we already know that temperature is a measurement of the average kinetic energy of particles. And when we talked about what it takes for a reaction to happen, for a collision to be successful, one of the criteria that needs to be met is that the collisions need to occur with sufficient energy. So a higher temperature means that your particles are moving faster, they have more energy, specifically more kinetic energy, which leads to higher energy collisions. So increasing the temperature tends to increase the rate of a reaction because it's essentially increasing your success rate. It is also increasing the total number of collisions a little bit, but that factor is nowhere near as important as the fact that a larger percentage of the total collisions are occurring with at least the activation energy, with enough energy to be successful. So more successful collisions is leading to a faster reaction. So generally speaking, higher temperature, faster reaction. And then the last factor we are going to talk about is the effect of catalysts on the rate of reaction. And you have likely heard of catalysts before as something that increases the rate of a reaction. So a catalyst has as part of its definition that it affects the kinetics. So a catalyst is anything that increases the rate of a chemical reaction without being consumed in the reaction, and that is important. So essentially your catalyst is still there in the end. It's kind of like a spectator ion, but it is actually involved in the process. It's just there in the beginning and there again at the end. So in a lot of cases, this means that your catalyst can actually be recovered and reused, which in a lot of cases is useful. For certain reactions, some catalysts tend to be very expensive. Platinum and palladium are both commonly used as catalysts for a lot of organic reactions, and those are both pretty pricey substances, so it's handy that you can take it back and use it over again. Since it's not consumed in the reaction, it's really not affected by it at all. There are a number of different ways that a catalyst can work. Usually, what's happening is that a catalyst provides an alternate pathway. So we're going to talk more later on in the unit about what's known as the reaction mechanism, which is actually the series of steps that a reaction goes through to convert reactants into products. So sometimes the catalyst provides a completely different pathway, also known as a completely different mechanism, that has a lower activation energy. Commonly abbreviated EA. So if a process has a lower activation energy, that means that more of your collisions are going to have enough. You have lowered the minimum energy requirement. So for instance, we looked at Maxwell-Boltzmann distributions a while ago now, where we looked at particle speed on the x-axis and number of particles on the y-axis. And our distributions in these usually look something more or less like this. So this is our distribution of speed, and we know that speed is related to kinetic energy. So let's say that our activation energy represents the kinetic energy where particles are moving at that speed that I just marked on the graph. That means that the only particles capable of colliding with enough energy are the ones to the right of that. So only particles that have sufficient kinetic energy can smash into each other hard enough to actually get the reaction to happen. If I lower my activation energy, sorry, didn't finish my thought there. If I lower my activation energy, by adding a catalyst, actually, I'm going to leave that there, just delete this. So let's say that this is our uncatalyzed activation energy. So the activation energy for the reaction with no catalyst added. When we add a catalyst, it's lowering our energy requirement. So maybe my catalyzed activation energy is over here. So the blue is the catalyzed version, which means since I've lowered the requirement, now anything to the right of that blue line is able to have enough energy to collide successfully and undergo reaction. Since we have more particles represented by the blue region of the graph here than by the red region of the graph here, the catalyzed process is going to be faster because more of our collisions are going to be successful. So it's important to recognize not just what makes a reaction faster or slower, but why in terms of the collisions. Is something creating more total collisions? Is it increasing the energy of the collisions, like temperature, which increases the success rate? Or is it lowering the energy required, like a catalyst, and increasing the success rate that way?